What if your car's battery wasn't just power, but the car's strongest armor? BYD did exactly that. Today we are pulling apart BYD's safety playbook, cell to body, and the E-Platform tree. I'll show you the engineering behind turning the blade battery into structure, the real numbers on stiffness and crash behavior, and why this matters for your safety, not just specs on a brochure. Stay with me and you will see how unseen engineering can change who walks away after a crash. Start with a simple idea. Most EVs bolt a battery under the floor like a luggage. We've already flipped that. With cell to body, the top of the blade battery becomes part of the car's floor and structure. That's not cosmetic. It turns the battery into a load-bearing element that raises torsional stiffness and reshapes crash energy paths. BYD and independent write-ups say this integration dramatically increases body rigidity and uses space better, which boosts both handling and occupant. Quotes torsional stiffness figures for models like the Seal at about 4,500 Newton meter per degrees, a number that sits in sports car territory that helps the car resist twisting forces in a crash or during evasive maneuvers. That stiffness is one tangible benefit of CTB or cell to body, and E-Platform 3. Euro NCAP results also reflect that design. BYD models built on this tech have achieved top safety marks with very high adult occupant protection scores in an independent tests. The battery itself plays a safety role too. BYD's blade battery performs strongly in extreme abuse tests. Nail penetration tests and crush or overheat trials showed limited smoke and no fire with surface temperature controlled in tests published. That's not a psychic, it's chemistry. LFP, lithium iron phosphate cells, are intrinsically more thermostable than many high nickel cells. And BYD's mechanical pack design channels and protects cells during intrusion. But there are caveats. Integrating the battery into the body means the battery becomes part of the crash structure. Great for stiffness and packaging, but it raises questions about repair, modularity, and crash energy management. If the battery is the floor, how do you safely repair intrusion damage? How do you balance a stiffness with controlled deformation so occupant energy is absorbed in a predictable, survivable way? These are real engineering trade-offs BYD had to solve, and the answers shape whether the tech truly improves safety across thousands of real crashes, not just lab demos. Let's unpack how BYD addresses those trade-offs. Cell-to-body improves structural integrity in three linked ways. It raises torsional rigidity, reduces the number of bolted interfaces with fewer failure points, and improved volumetric utilization of the packs so engineers can shape crash paths around the cells. BYD claims higher volumetric efficiency and industry analysis suggests cell to cell to body can push pack utilization significantly compared with older designs. That matters when you want a low center of gravity and clean crush zones. On thermal safety, the blade battery's nail penetration and oven tests are important because many EV fires start from the internal shorts or thermal runaways. BYD's test results show limited temperature rise and no sustained fire in extreme lab abuse, indicate the blade battery cell chemistry plus mechanical design resist propagation. That doesn't mean fires are impossible, but it gives the pack a higher margin in real-world abuse. Crash performance in real labs and regulatory programs matter most. BYD vehicles built on the E-Platform tree have posted very strong crash results in Europe and other markets, with high scores for adult occupant protection attributed in part to the cell to body. That's independent validation that structure plus safe cells produce safer outcomes when car is properly engineered end to end. There's also a systems side. Safety isn't only metal and chemistry, but BYD pairs cell to body with active systems, thermal management, and multiple layers of cell protection inside the pack. 10 layers of protection in some commercial packs, robust cooling channels, and an integrated vehicle control strategy all work together to reduce risks. Think of it like layers of defense: chemistry, mechanical design, structural integration, and smart electronics. Here's the moment that ties it all together. When a crash energy hits the car, two things matter most: where the energy goes and whether the battery becomes part of the problem or part of the solution. BYD's approach intentionally makes the battery part of the load path. So instead of the battery being crushed and creating a hazard, it helps carry a load in a controlled way. When tests and real world safety scores show that, when done right, cell to body plus blade battery can reduce intrusion and protect occupants not by magic, by engineering a predictable structure backed by more stable cells. That's revolutionary because it changes the fault tree. Fewer surprises, more controlled outcomes. Two quick figures to remember. BYD reports the blade battery surface rose to only 30 to 60 degrees centigrade in extreme nail tests without any fire. An E-Platform 3 car show step change stiffness numbers that put them in a different class for occupant protections. Those are the hard signals that the approach is doing real work. So what's the bottom line? BYD's cell to body and E-Platform 3 are not just marketing phrases. They're a coherent safety strategy. Stable LFP chemistry, mechanical pack designs that resist propagation, and structural integration that rises rigidity and helps control crash. The results we see, strong lab abuse tests and high independent crash scores, make the claims credible. These trade-offs around the repairability and standardization are real, but the safety gains for the occupants look tangible.